Okay, so hello everyone. Hope you enjoyed the lunch and welcome to the technical session number 3, the EMI Analysis and Mitigation. And my name is Chang Li. I'm a social professor in CPES, and I will be the session chair. So in this session, we will have 3 technical presentations. And after each presentation, we will go to, after each presentation, we have the Q&A. And after this session, we have a dialogue session in the CPES lab, okay? So the first presentation, the title is Noise Propagation Study on Gate Drivers Caused by Near Field Coupling Inside the Medium Voltage High Power Silicon Carbide-Based Converters. And the presenter is He Song. And he received his bachelor degree in electrical engineering from Chongqing University, China in 2013, and his master degree from the University of Michigan in 2018. Right now, he's a PhD student in CPES, and his research interests include the high power medium voltage magnetic design and the EMI considerations. Okay, please, He.
Good afternoon, everyone. My name is He Song, and today I will be talking about the noise propagation study on gate drivers caused by the near field coupling inside the medium voltage, high power silicon carbide-based power converters. Today, I will start with a short introduction, including the motivation, the background of motivation of the work, and followed by our proposed high-level methodology and the noise propagation model caused by the near fields. After that, I will show some experimental results, including the experimental validation of the proposed model, the interaction between noise caused by both fields, and the factors that influence the noise propagation. And finally, the summary and the conclusion. As you all know, the medium voltage converters have been widely used in recent years. Here shows an example of a power processing cell inside the medium voltage MMC. As you can see, there are many subcomponents inside the power converter, such as gate drivers, controllers, sensors, etc. So they are arranged in a very compact way to increase the power density of the converter. Among those components, the gate driver is something that we are looking at in this presentation. As you can see in this real image, we can see the gate driver for this 10 kV power module, and those 2 PCBs are the gate drivers that are designed for it. In the normal operation, we found some issues. For example, the gate driver sometimes trips during the normal operation, especially the high side gate driver and especially under the higher dVdt. That shows strong evidence to the EMI issue. When it comes to the power electronics EMI, there are all kinds of, we know that there exist all types of EMI standard that regulates the noise, that regulates the EMI emission at the converter terminals. So those are all the converter level EMI. However, even if a converter satisfies with a certain EMI standard, it's not a guarantee that all the components inside the power converter can without any issue. So that's to say, we really need to figure out how the noise is propagated inside the power converter. That is one thing. On the other side, the gate drivers in modern medium voltage power converters usually employ very complex design to achieve very comprehensive functionality. That's to say, it has to be very immune to the EMI inside the power converter. Right now, people already know that the main circuit fast switching will cause the induced common current propagate on the gate driver PCB, and people try to minimize this common current as much as possible. However, by saying minimizing, there's no criteria of how small the noise is good enough. In order to answer that, we really need to look into that and figure out how is the common current is related to the malfunction of the gate driver. So all these questions are the motivation of this work. Specifically, in this work, in this presentation, I will be talking about the noise propagation on this highlighted printed circuit board. As you can see, since it is designed for parallel power modules, there are 3 channels to be connected to the power module. And it is a smart gate driver. As you can see, there are a lot of signal processing circuitries routed on this gate driver on a separate ground. I will talk more about that later on the next slides. Here on this page, I will show our proposed high-level methodology to address this issue. before I do that, I would like to shortly introduce the power architecture of the gate driver that we're using in our projects. As you can see here, those diagrams shows the gate driver PCB that I showed in the real image on the previous page. For each gate driver, as you can see, there are two grounds on the PCB. The red ground is called gate driver ground, or GDG in short. The reason it has the name is because it is directly connected to the power module. On the other hand, we have a signal processing ground, or SPG in short. It is isolated from the gate driver ground. For all those sensitive signal processing circuitries, they will be routed on the signal ground. So since the Kelvin source of the top device is a jumping node with pretty high dV/dt, the direct consequence of this fast switching of the main circuit is that it will cause a common current to flow on this ground planes of the PCBs. As you can see here, this blue arrow is the common current. And we kind of isolated the signal ground from the gate driver ground. In that way, we can minimize the common current that flows on this yellow ground. So all that I have just talked about is about the conductor EMI, and it has been widely studied in previous research. So it's not the focus of the study. And we summarize it as level 1 of the methodology. Moving forward, what we are interested in is the noise induced on the signal traces of the gate driver. Let's take a example. So here, as you can see, there is a signal trace that is routed on the signal ground, and IC1 generates a very clean signal. However, at the receiving side at IC2, what it receives is a noisy signal. As you can see, as long as there is a switching event in the main circuit, there will be some noise induced. So this noise is something that we are concerned about. So this noise could be caused by the common current on gate driver, by magnetic near field coupling and conduction, or it can also be caused by all the high DIDT objects via magnetic near field coupling, or it can also be caused by the dV/dt itself by the electric near field coupling. So this is the level 2 of the study. Level 3 of the study, so once this noise exceeds the threshold value of the signal receiving IC, false triggering will happen. That is the level 3 of the methodology, and it is also known as the IC level susceptibility. Among all these levels, level 2 is something that we are focusing on, which is the noise on the signal trace. In order to study the noise on the signal trace, we propose this trace plane noise propagation model. The noise is mainly caused by the near field coupling. For the high DIDT objects, they are associated with the magnetic near field coupling. For the dV/dt, it is associated with the electric near field coupling. Let's start with the magnetic near field coupling. Again, here I show the top gate driver and bottom gate driver. Let's zoom up the top gate driver to see some more details. As I said before, the red ground is the gate driver ground, and as I said before, there are 3 channels to be connected to the power module. So the noise source will be the VDS of the bottom device. On the other side, we have the power supply for the gate driver. So based on that, the common current will be induced and flow on this gate driver ground. As you can see, if we use different channels, it will significantly influence the common current distribution. And as I said before, we have a signal processing ground, which is isolated from the gate driver ground by this isolated power supply and the gate driver IC to minimize the common current on it. And here I also show a signal trace routed on the yellow ground. So I want to mention that the signal loop is formed by the signal trace and the partial signal processing ground between the grounding point G1 and G2. So this forms the signal loop. And on one side of the trace, it is the RS. That is output impedance of IC1. On the other side is our termination. So that is a terminating resistance on the other side. And we also have this reference ground plane. So it is the reference potential of the converter. So for example, it could be the DC bus bar in a real circuit. So for the terminating resistance, it's usually pretty large. So the current flow on the signal trace is usually pretty small. So the voltage drop on the RS can be negligible. In order to solve the noise, which is shown here, we need to use the KVL to find it. So we need to find out the voltage across the signal trace and the voltage across the partial ground plane between grounding point G1 and G2. And these two voltages behave like a cancellation effect. It will be the subtraction of these two voltages. So as for the cost of these two voltages, the first cost is very simple. It's the ICM on the gate driver ground, because it is much bigger than that on the signal ground. It is caused by these two mutual inductances. So based on MDI/dt, it will induce the voltage on these two objects. And I also want to point out that the subtraction of these two mutual inductances is exactly the mutual inductance between the signal loop and the power ground. And that is a very crucial parameter in noise coupling. On the other hand, we have the second cause of this voltage, which is the ICM on the signal ground itself. So again, the mutual based on the voltage across the signal trace will be caused by the mutual inductance based on MDI/dt, and the voltage across the signal ground plane between G1 and G2 will be caused by the conduction. So finally, the noise will be the this voltage minus this voltage based on the KVL law. So in the end, we can get the final expression of the voltage that is caused by the near field, the magnetic near field coupling as shown here. Again, this parameter represents the mutual inductance between the signal loop and the power and the gate driver ground, and it is the most crucial parameter in the noise coupling. Now let's move on to the electric near field coupling. The story is totally different. The electric near field coupling is caused by that the gate driver is connected to the high DVDT node and those parasitic capacitance between the PCB and the reference ground. So there will be some displacement current induced, and there will be some voltage induced between the signal trace and the PCB ground. So the equivalent circuit will be shown here. So the top gate driver ground is connected to the high DVDT node, and so again, the VDS2 will be the noise source of this noise coupling. And in this case, the planes and traces are modeled as lumped nodes, as you can see here. And also the reference ground here is very crucial because that will define all those parasitic capacitances. Lastly, this RS and our termination will be regarded in parallel, and this parameter is also very crucial in this noise coupling. Let's first roughly estimate the noise. Under transient, this circuit will be like a capacitive voltage divider, so we can derive the noise as negative ratio times VDS2, and the ratio is between VTG and VTP. CTG and CTP, where CTG is the parasitic capacitance between the trace and the reference ground, and CTP is that between the trace and the PCB ground. Under steady state, this voltage will be zero. So there is a decay with that time constant formed by RTP and CTP. So that is roughly a rough estimation. So specifically, we can solve this specific time domain expression for the noise using the inverse Laplace transform. So the first term is the same as here, and the second term involves a decay with time constant here. Now, let's combine the two equivalent circuits to get the final equivalent circuit for the noise coupling. And for both near field coupling, they have a common noise source, which is the VDS of the bottom device. For the magnetic near field coupling, first of all, we have ICM equals CdVdt, and the noise is MDI/dt. So there are two derivative steps here in this flow. For the electric near field coupling, it is negative constant times the VDS2 with a certain decay. So in the end, we can add this voltage up to get the final expression of the voltage caused by both near fields. Starting from this page, I will show some experimental results. First of all, I would like to show the experimental validation of the proposed model. Here, a buck converter serves as a high DVDT source, and the DVDT can go up to 50 volts per nanosecond. In this setup, there are two gate drivers. The first one is the actual gate driver, the functional gate driver that actually drives the power module. On the other hand, we have a test coupon PCB that is for noise measurement purposes, and it is not a functional PCB. And I would like to mention that the test coupon is placed in the shielded box to get rid of the influence of the near field caused by the rest of the circuit. As you can see here, the reference ground plane is tied to the negative rail of the DC bus. And also I want to mention that for the trace under test, at one end, it is connected to the ground plane via this RS to represent the output impedance of IC of the IC. And on the other side is the measurement side. Here shows some measurement. So here in the experiment, we measure the VDS2, which has a pretty high dVdt. And we can also directly measure the ICM flowing through the test coulomb PCB, and we can calculate the dIdt using MATLAB. And we can also measure the real actual noise by this isolated voltage probe. And this is the measured noise. And based on the equations that are shown on the previous pages, we can calculate the noise using this waveform. As you can see here, shows the comparison between the calculation and measurement. So they are in very good agreement in terms of a peak value, decay, and raining. So this is the validation of the proposed model. Here, I would like to mention something more about this RS. In this experiment, the RS is a simple resistor to represent the output impedance of the IC. In the real world, the output impedance of an IC vary widely. For example, it could be several ohms. It could also be several hundreds of ohms. And if this RC equals 0, the noise is only caused by the magnetic near field because the signal loop still exists. If we increase the RS value, the influence of electric near field will become stronger and stronger. And I will show that transient in the next slides. So as I said before, by changing RS, we can change the transient between the H field coupling and the E field coupling. So before I show the waveforms, I would like to put two waveforms as a reference. So here is a dIdt waveform, which is an indication of magnetic near field coupling, and here is the VDS2, which is an indication of the electric near field coupling. Again, for the magnetic near field coupling, the key factor is the mutual inductance between the signal loop and the power ground and the gate driver ground. For this mutual inductance, it could be either positive or negative. It is up to how the trace is routed. However, for the electric near field coupling, it is always negative. Now let's look at the result. So here shows the measured noise waveform of an example trace with different RS values. As I said, when RS equals 0, it is only influenced by the magnetic near field coupling. So as you can see, the waveform is like a reflection of the dIdt waveform, just like the polarity flips over. The reason it has the opposite of polarity is because for this trace, the M, this mutual inductance is negative. If we gradually increase RS value, we can see there will be a high frequency noise superimposed on this waveform. And this high frequency noise is the reflection of VDS2, and it is caused by the electric near field coupling. So here shows a clear trend between magnetic near field coupling domination all the way to electric near field coupling domination. And since for this trace, both two voltages have the same polarity. So if we increase RS, we can see the peak value goes down all the time. So these two noise behave like an addition effect. Now let's look at another example. So for this trace, the difference is that the mutual inductance is positive. So that's why the noise waveform has the same polarity of the dIdt here. So again, as we increase RS, we can observe a stronger electric near field coupling impact. Since these two noises have an opposite polarity, that's why you're seeing that the peak value first going down, then it goes negatively higher and higher. So for this trace, these two noises behave like a cancellation or a counteracting effect. Now, the last piece of my presentation, I would like to show some factors that influence the noise coupling. I'll start with the magnetic near field coupling first. So as you can see, I selected 3 traces typical trace to study. Again, the test coulomb is placed in a shielded box, and in the experiment, we can use any one of the channels to connect to the power module. Since we're looking at the magnetic near field coupling, we just short this end of the trace and measure the voltage at the other end of the trace using a SOV probe. At this time, so for this case, only the noise peak is recorded and compared instead of the whole waveform, instead of the detailed waveform, because it's more of a comparative study. And I summarize all the test results in this chart. Let me explain it a little bit. For the horizontal axis, it shows the result of different channels when different traces are tested. So as you can see here, it shows the 3 traces when 3 different channels are used. And for this axis, it shows different dVdt values. And on the vertical axis, it is the noise peak, measure the noise peak value measured in millivolts. So first of all, we can observe 2 general trends here. The first general trend is that the noise increases with dVdt, and that is pretty straightforward. Secondly, we can observe that if we change from channel A all the way to channel C, the noise usually increases. That's because when channel C is used, the common current will cover more area on the gate driver ground, and that will lead to more coupling, stronger coupling between the signal trace and this gate driver ground. Now let's look at trace 1 specifically. For trace 1, it is highlighted here. So as you can see, it's a pretty long trace, and it is almost parallel to the ICM propagation path. So that's why it picks higher noise. However, for trace 2, it is shorter in length, and it is perpendicular to the ICM propagation path. So that's why it picks up lower noise. For trace 3, it is located on the gate driver ground. Although it is very short, much shorter compared to trace 1. However, as you can see, when channel C is used, the noise is not very small. As you can see, the noise is almost half as that of trace 1 measurement. So as a conclusion, what matters here is that the trace property, including location, length, orientation, because that will influence the mutual inductance between the signal loop and the gate driver ground. Move on to the electric near field coupling. As I already showed you before, if we increase this RS value, we will observe that the noise peak will increase. Besides that, I would like to pick this column as another example. So for example, for this column in the experiment, if I change the distance between the PCB and the reference ground, converter reference ground, the measured noise will change accordingly. That's because when I do this, I will change the parasitic capacitance between the trace and the converter reference ground. So that's why in the formula I showed before, that will also change the noise measurement. So what matters here is that, first of all, the resistance between the trace and the PCB ground, which is the output impedance of the signal generating IC, and also the distance between the PCB to the converter reference. To conclude this presentation, a generic methodology is proposed to study the mechanism of how the fast switching of the main circuit causes malfunction of the gate driver via near field couplings. A trace plane noise propagation model combining both magnetic and electric near fields is proposed to study the noise on the signal trace and experimentally validated. Interaction between the noise caused by both fields is also investigated. Sometimes it behaves like an addition effect, and sometimes it behaves like a counteracting effect. Factors that influence the noise propagation is also studied. For magnetic near fields, the mutual inductance between the signal loop and the gate driver ground is crucial. For example, that's to say the trace properties such as location, length, orientation, etc. That all matters. For the electric near field coupling, the impedance between the trace and the PCB ground matters, which is the output impedance of the signal generating IC. Also, the parasitic capacitance between the trace and the converter reference ground is also crucial to the noise propagation. So that's it for my presentation. Thank you very much for your attention.